All right, so we move into the material covering fluid statics. Statics, just like the class statics, engineering mechanics statics, things don't move. Fluid is at rest, stationary fluid. So we understand that before we move into the more difficult material, or challenging, or some may say interesting, where fluid is moving. We already talked about pressure, did we not? Force per unit area. We also talked about units of pressure, a lot of units, Pascal, kilopascal, megapascal, bars, PSI, ATM, torr, there's many units of pressure. Barometer, what does a barometer measure? Atmospheric pressure, the local atmospheric pressure. Sometimes in the newscast they'll say the barometer is rising, the barometric pressure is rising, barometric pressure is falling. Manometer measures pressure difference by a fluid height in a column. Borden tube, it's a very common mechanism to measure pressure, invented a long time ago, still in practice. So it's a C-shaped tube that often subjected to increasing pressure, it tries to stretch and become straighter instead of C-shaped. That's all material we've covered. Today we move into Pascal's principle, hydrostatic forces on planar surfaces, curved surfaces, center of pressure, review of area moments of inertia, parallel axis theorem, etc. So let's just jump into it. So we have hydrostatic pressure in a non-moving or stagnant fluid. First concept is the pressure is in a fluid at rest is the same in all directions. So if I have a fluid, I talk about the pressure at this point right here. If there happens to be a solid surface cutting and the fluid is on this side, it has a pressure at that point that's equal. Let's say the surface cuts and is at this orientation. Well, the pressure is the same value. It doesn't matter on the orientation of where there may be a solid in that submerged fluid, submerged in that fluid. Okay, so it's if I have a solid surface submerged in that fluid at that point, whatever the orientation of the surface is, the pressure is perpendicular to the surface and has the same magnitude. All right, the pressure in a fluid at rest increases with depth, and we've used that equation, rho GH. How do we derive that equation? Do a free body diagram of a little column of fluid going down. Let's just go down from this surface down to a depth h. A very thin little column. Do a hydrostatic force balance, right? You have the weight going down. You have the pressure on that little area acting upward, the pressure on that area acting downward. Often that's the atmospheric pressure multiplied by that area. Let the area be very small, or we're going to cancel it in a minute. What about the weight? That's acting downward too. And so the weight is the product of the mass, which is the mass density of the fluid, times the height times that cross-sectional area. That gives me the volume. Rho V gives me the volume, and then multiplied by rho, that gives me the density. The density gives me the mass. Multiplied by G, and that's the weight. True? Did I get the right weight correct? Give me a thumbs up if you like the weight. Everybody else, good? Does it look good? No thumb on you? You got a thumb? You got a smile? That's good. All right. Those are acting down, and then the pressure at that depth times the area acting up. We cancel the areas. And if you say, hey, I'm interested in the gauge pressure, then the pressure is equal to rho G H. Let's say I want the absolute pressure, well then I have to add the atmospheric pressure on the top of that fluid column. Rho GH. Rho GH. Did I encourage you? A lot of people like tattoos. Get some engineering tattoos. Why not Rho GH on it? I heard in the prison system some gang likes to tattoo 210 as the area code for San Antonio. I mean, tattoo something else other than the area code 210, you know? Some prison gang or something, I don't know. I've not been in prison, sorry, that's not from personal experience. So anyway, so now let's consider this. Let's consider a column. If somebody says, if this height of the fluid H, what's the pressure at the bottom? Rho GH. Aha, now we're going to change it and give you a different shape. So the height of that fluid column is H, but it's a different shape. It's a wedge shape. And so we just said that the pressure, rho GH, is due to the weight of the fluid above it. It looks like the pressure in this case, let's call this case B, and let's call this case A, and then this case, case C, pressure case C. So case A, case B, case C. We said the pressure is due to, in fluid statics, is due to the weight of the fluid above it. I look at it, I say, aha, this one has an increasing area. I've got more fluid above me. It must have a greater weight or a lesser weight. So that's our first clicker question for today. Which one it has the greatest pressure? Which is the highest pressure? Is PA the greatest? Answer A. PB, come on now. Pressure at B, is that the greatest pressure? Pressure at C, is that the largest? Or answer D, they're all the same. So clicker question, and we start it. So if you think pressure at A for case A, remember these are all the same H. I haven't changed H. Which pressure is the highest? Highest. Is it A, B, C, or answer D if you say, hey, they all have the same pressure? And we'll take a look at the results. And the results are that people say that they're all the same pressure. 86% correct. Okay? So some people maybe thought C was different. Why? Well, it looks like it's a greater funnel. It's holding up more. True? But you have to think about the force. There's a pushing back from the wall onto the fluid to restrain it, to hold it in place. True? And you can decompose that into a lift as well as a push to the side, that force. And that helps hold up some of the fluid. So no. It's same pressure. Same pressure. Okay? All right. Let's do this. If I compare points A, B, and C, which one has the highest pressure? C. If I compare D with A, do they have the same pressure? But D is on a solid surface right there. Does D have a lower pressure? Same pressure as point A. Same pressure. I have a concrete, heavy protrusion, okay, that's sticking out right here. And so point E is the fluid right underneath that heavy concrete protrusion. If I look up from point E, I've got to go straight through concrete before I get back into the fluid. Is the pressure at E the same as the pressure at B? Greater than the pressure at B or less than the pressure at B? The same. That tricks students up. There'll probably be a FE exam question that tests your application of these principles. And the typical question goes something like, they give you a big container, and let me just give you kind of part A and then part B. And then they'll have some sort of surface right here and go down, and they'll say pressure at A versus this pressure, and the fluid is at this level, right? They're the same pressure. It doesn't matter that one is at a surface that's oriented at a slant, okay? This pressure in the fluid right here on this wall that's vertical versus a wall that's sloped, they have the same pressure if they have the same depth. And then they have it where, okay, we come like this, we come underneath. This is all just like I set it up. And they say, okay, what about the pressure here versus the pressure here? Same pressure. What they do is they'll change it up a little bit, and they'll have maybe it go down like this, and go back up, and then go down like this, and then go back up, and the fluid, let's get rid of this, the fluid level comes across. And all of that is water, but they put some mercury. They spilled some mercury in it first, and mercury is dense. It sinks, but it's still a fluid. And so all of this is mercury, and then they do this. They say, what about the pressure at this point versus the pressure at that point? Fluid's not moving. Fluid's static. You have the water here. True. This is all water here, but you have mercury there. Which one has this? Do they have the same pressure, point A versus point B? Or is the pressure at B higher? B is higher. In that case, B is higher. Okay? True? Somebody has a above ground swimming pool. Here's my swimming pool. It's above ground. Here's the ground. And so the water level in the pool is right here. That's the water level in the pool. Somebody says, I'm going to jump off the pool and I'm going to lay right here on the ground outside the pool. There's my rendition of a person. Or I'm going to jump in the water and go to the bottom and lay at the bottom of the pool. Does the person inside the pool feel the same pressure as the person outside the pool because they're at the same depth, so to speak? Well, yeah, but one is fluid, depth of fluid, and the other is depth of air. So, no, they're not. That's the same principle as this one. Okay? Pascal's principle. So for a confined fluid at rest, it's not accelerating. It still can be moving, but not accelerating, or minimum acceleration forces. A lot of times we can apply static principles to dynamic problems as long as there's not a lot of motion, okay, or not a lot of inertia or acceleration. Okay. So if you have a confined fluid at rest, if the pressure is increased in one part of the fluid, then that pressure increase is felt throughout the fluid. Everywhere in the fluid will feel or experience the same pressure increase. So think about I have a piston, I seal it up, the fluid's all confined. I know that the pressure right under the piston at that point A is less than the pressure at B. And the pressure at B is greater by rho GH, right? The H. But if I push down on the piston to boost the pressure underneath the face of the piston, that boost in pressure is experienced also at B. This is a principle hydraulic systems. Okay? Hydraulic systems. So here we see the mechanical advantage of a hydraulic system. Think about a piston connected to a fluid system. The piston over here has a small area, A1. Over here it has a large area, A2. So if I push down with a force F1, doesn't it increase the pressure underneath the piston by the amount the pressure? I'm just thinking of pressure increases. The force is at F1, force 1 divided by A1. That would be the increase. Okay. Well, if I push down with, I don't know, let's pick a value, 1 kilonewton here, will a force 2 of 1 kilonewton suffice to hold the second piston at the same location? Or will it have to have a larger force to keep it? It'll have a larger force because the increase in pressure from Pascal's principle, the pressure increase is the same. So the pressure here is F1 over A1 by consideration of the piston there. And we look at a free body diagram of this piston, that's equal to F2 divided by A2. So if I apply a force F1, it's as if the magnitude of the force is increased by an area ratio, that's the mechanical advantage, such that F2 has to equal or will equal A2 divided by A1 times F1. So if I have a 10 to 1 mechanical advantage because of cross-sectional area of the piston's larger, then to hold it there, it'll be 10 kilonewtons. 1 kilonewton will be able to exert a force of 10 kilonewtons somewhere else. You ever use hydraulic jacks, jack up a car? Isn't that incredible? Little motion like this lift something that weighs a lot. Or you watch the guy in the machine shop or automobile repair where they lift the car. This is it. Or front end loaders and other little cylinders with the hydraulic systems on machinery. Very powerful hydraulic systems. So what principle is used in hydraulic systems? Pascal's principle. What's it say? Confined fluid. If I boost the pressure in one area, the same pressure increase is felt in another area. How do we use it? Change the areas of pistons, and now you have a significant mechanical advantage. Let's now move into fluid statics. Let's talk about this theoretical problem as an introduction to the topic. I have a fluid. It's a lake or something. I have the bottom of the lake, and then I have a pipe protruding up from the bottom of the lake, and so it's air inside this pipe and air outside the pipe. I have a lid that sits on the top. I've color-coded it red, and I look at a cross-sectional view of it, and you see it's a circular lid sitting on that round pipe. It's at a constant depth H1 in the fluid. So everywhere along that lid, it feels the pressure downward from the water pushing down. So what is that uniform magnitude of the pressure on the top of that red circular planar surface, a submerged lid? It's equal to the density of the water, G H1. I want to take that distributed load, just like we did in statics when you took statics class, and I want to replace it by an equivalent point load, the resultant system, distributed load to a single force. Well, I would say I'll put one force of magnitude F of R, the resultant force. What is the magnitude of that resultant force? Well, it would be the pressure times the area, or it would be rho G A1. This is a bad looking H. That's H1. Rho G H1 times area. And that area, if I have a disk of diameter B, then the area is pi B squared over 4. That's the area. So rho G H1 times the area gives me that resultant force. That's the magnitude of that resultant force. Where would I want to place it? Would I want to place it offset somewhere? Put it here? No, you would put it right in the center. Right in the center. So the location of placement would be right in the center of that disk. Let's change it up just a little bit. Let's take a look at not the system we just analyzed, but let's look at a hypothetical system which is a pipe that's not round. It's a triangular pipe. You can't buy one. Let's just talk about it. It sticks up into the fluid. True? And so I look down a cross section. It looks like this. It has a base A and a height B. Those are the two parameters, A and B. Now, I say to myself, can I replace, well, first of all, can I get the pressure at that face? Yeah, that pressure is rho G H1. Hasn't changed. Can I get the magnitude of the resultant force to replace that distributed load by a single point load? Yeah. What would be F of R? It would be rho G H1 times the area. The area, what is the area of a triangle? Yeah, these are another thing. I hate to, but we had a discussion, Professor, what am I liable for? You have to know the area of a triangle. I'm not obligated to give you the equation for the area of a triangle in an exam, or the area of a cylinder, or area of a sphere, etc. Okay? Or the volumes of simple geometry, some things we just got to know. So base of A times the height B. Did I do that correctly for f of r? Now the difference. Okay? Where do I apply it? Should I put it right in the middle? Nope. Because if I put it right in the middle, it'll look like that. So where do I put it? Well, I put it on a line that goes this way through the middle, so to speak, right? Somewhere along that line. But I don't put it at location b over 2, do I? Put it at b over 3. How many people knew that? B over 3. How did you do that? Memorization, huh? Center of gravity. Another way, how did you derive that? That needs to be placed at the location b over 3, which probably I didn't draw too well. Put it right about right there. Okay? So it gets at that point right there is where you have to apply it. Okay? Right there. What principle in statics did we use to derive that result? And the first time you saw it, you probably shook your head and said, wow, this is something else. But you use it a lot in engineering. Yeah, in statics we had 3 big concepts. Sum of the forces, well, I'd say 3. For 2-dimensional problems, in equilibrium, sum of the forces and the y, those are 2 big concepts. In 2D problems, what else? What else did we use to say? Sum of the moments. Sum of the moments. Do you remember that? The sum of the moments about particular point has to be equal to 0, just like the sum of the forces in x, sum of the forces in the y. Now, I know for 3D, you can have 3 force equations and 3 linear momentum, or not momentum, moment equations. But in 2D, just think 2 force, 1 moment equations, okay? Okay, and you think about moments about a point in 2D. In 3D, you think about moments about lines or axes. So that's how you got it. You got it from that principle, didn't you? Mm-hmm. Let's take now a look at a vertical surface. So I'm interested in the equivalent resultant force that the water exerts. The water is only on the left side of this vertical surface. I color code it red right here. And also I give you a different projection. So if you wanted to, this length is h, and maybe it goes into the board a distance w for depth or something, or a or some other parameter. Okay? You can't see it, but it's into the board in that dimension w. Okay. So first of all, we'll look at just the gauge pressure, and it's a distributed pressure load. It's lowest at the top. The pressure at the top is 0 gauge. And the pressure at the bottom is the highest. It's rho GH. True? Rho GH. So the question is I want to replace this distributed load by a resultant force, F of R, that's going to act in the positive x direction. It's going to be pushing that way. Okay? What is the magnitude of it first? And then where do I place it on that face of that plate? So what is F of R, the magnitude? Yeah, a lot of times I like to break it down a little easy. Something times area. How about a pressure times area? And then this pressure is probably some average pressure. Okay, some average pressure times area will give me the force. True? Okay. If I didn't think that gravity was working this way, and if the pressure distribution was really a rectangle and not a triangle, and it was equal magnitude regardless of the height, That's an easier problem, isn't it? That would be then, that average pressure would be just the pressure rho GH and then multiply by the area. But I don't have a rectangular where it's all rho GH. I have it going from 0 at the top to the maximum at the bottom of rho GH. But guess what? Yeah, I mean, we can do the calculus, and we will do the calculus in a minute, but just engineers, if we can avoid the calculus, we'll avoid it. So, isn't it half? Isn't it 1/2? Because if I take a box like this, and I throw away this half, I just threw away half of the load, half of the force to the right. That makes sense? So, one way to look at this is to put that half under this H. And this average pressure can be interpreted as the pressure in the middle. In the middle, where this distance is H over 2. Okay. I know this is a rectangle, but what would we call this point right there? This point right there. Can you see it good? Does it change of color? We would call that, the point is the center of the area, or center of mass, but I'm just talking about the area that it applies to. Sometimes we'll call that the centroid. Familiar? So if you wanted to calculate F of R, what you would do is you would say calculate the pressure at the centroid and then multiply it by the area. And for this problem, the area is just W times H. Okay? Okay. I know I didn't give an illustration where I show a different red-colored surface. Let me try and do this. Let me try and say that this surface is red. I'm going to clip those off, and I'm trying to make it symmetrical here. And so forget about this triangular part to the red and this triangular part to the red. Okay? The location of the centroid kind of in the x direction hasn't changed. It's symmetrical. I'm trying to draw it symmetrical about that. But did the location of the centroid change to shift up, stay the same, or shift down from the original location? It shifted down a little bit, true? So you can have a planar surface that's not rectangular and solve this problem, but you got to get the pressure at the centroid of the area. Okay? Now, we can do more mathematically, but I want to make sure and not lose sight of the physics before we do it with the integration and the calculus. All right. Before I move into beating up or moving into the integration and the calculus, let's back up to our plate here. Okay. And ask, now that I know the magnitude of F of R, and I even know conceptually how to calculate it, get the pressure at the centroid of that area, and multiply it by the area, boom, I have the magnitude of F of R. Okay. Where do I apply it? I'm going to use moment considerations to figure out where I apply it. Do I apply it at H over 2 down, right in the middle? Or do I apply it at 2/3 H down, right in the middle? We're going to vote. Apply it here, case A, or apply it there, case B. We get to vote, and we're now counting away. Or do you want another alternative, C, none of these, somewhere else, but not there, not A or B? 7 seconds, running out of time.
This asking where we're going to place the centroid.
It's a square. The red area is a rectangle, square. I shouldn't say square, it's a rectangle. I didn't say the width was the same as the height. It's a rectangle. Where do I apply f of r? We now know the magnitude of f of r. Where do I put it? Okay. Okay. Yes, sir.
If the pressure lines were vertical instead of horizontal, would we be taking the area of the triangle instead?
I think I know where you're going, but let me just answer my simpler question, okay? And then maybe I'll try and backtrack to your question. All right, so let's see where we're at for responses. Well, we're pretty good. We're 87%, but 6 people and 13% of the class think it should be put at the centroid. But you don't put the resultant force at the centroid. Where do you put it at? Because it's a distributed force field that's not uniform, it's triangular shape, you put it 1/3 from the base or 2/3 from the top. Okay? So you need to not put it right in the middle. You put it right about there. You put it right around point B. So it's symmetric here, but it's 1/3 up or 2/3 down. Did that make sense? Okay. This is always confusing to students. A short way of calculating f of r is to get the pressure evaluated at the centroid of the area. And the area, when it's a rectangle, well, that's pretty easy. The centroid is right in the middle. Okay. But if you start to change the shape of the area, it pushes the centroid down a little bit. Okay, just like I mentioned. But it's still, to get the average pressure for this planar surface, just get me the centroid of that planar surface, then get me the pressure at the centroid. Okay? Then multiply that times the area, I have the resultant force. But that's not the same now. Now you have a different question. Where do I apply it? Where do I apply it? And you don't apply it at the centroid. You apply it where you have a moment balance to give you the same resultant rotational, it's a moment of a force that measures its tendency to make the system want to go in a circle, to rotate. And for a static problem, it's not rotating. The sum of the moments is equal to 0. Okay? So we apply it at this distance, 1/3 up. Okay, now, you may have, this is a tough one. I don't know if I should try to avoid your question or not. But somebody says, if I look at the force on the side, projection of the force, you know what I have? I have a triangle. True? I have a triangle. That's not a geometrically physical where I can go out and touch it. The red surface I can go out and touch. That's a rectangle. Okay? But geometrically, there's a triangle. And what I think you were asking me is can't I calculate the centroid of the triangle? True. Where would the centroid of the triangle? I know it's not a physical area, but where's the centroid of this triangle?
The y component would be 2/3 down.
It would be right here, 2/3, 1/3. It would be right here, 1/3, 2/3. Right there would be the centroid of the triangle. True? That is the triangle is of the pressure distribution, and the resultant force goes through the quote-unquote centroid of the triangle force distribution.
But I don't want to apply my resultant force.
No, that's where you apply it. It goes through that line of action, but you don't want to calculate the resultant force that way. You want to go to the physical, I can touch it area and get the centroid of that area, get the pressure at the centroid multiplied by the area. That's right, that's the average pressure. Why did I start off with, this simple case? Go back and review the simple a couple times and then move forward, okay? Because it's not, it doesn't take much before you need to be careful. There's opportunities to make errors. All right, are we ready to press forward for this one? So, in summary, to get an equivalent force system to replace that hydrostatic distributed load on the wall, on the surface, calculate F of R. When you think about calculating F of R, get the pressure at the centroid of the area. Second, if you want to know where to apply it at what they call the center of pressure. And the center of pressure is not where you evaluate the average pressure. Often the pressure is increasing as you go deeper into the fluid. The center of pressure is below the centroid. Okay. For this problem, it was evaluated at 1/2 the depth to calculate the average pressure, and then to apply it, it's at 1/3. Now let's do it a little more mathematically, and while we're at it, let's do it for a surface that's not vertical or horizontal. It's at some orientation, but we need to leave it to be a planar surface. What does it mean when it's a planar surface? It's not curved. It's just flat. That planar surface could be a rectangle. The planar surface could be a cylinder. The planar surface could be a triangle. The planar surface could be some geometric shape, but it needs to be flat, true? But I'm going to put it in submerge it in some fluid, and we'll put it at an orientation phi. And we'll start the measurement of a coordinate system y at 0, the origin, so to speak, and go down, 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 down. And now this is the start of my planar surface at location y1. And it goes to location y2. And then I'm just continuing the axis y deeper into the fluid. But that's my surface. I kind of roll the surface and give you a projection of it. Okay? When I look at the surface, see what I'm doing there? I'm changing the orientation to help see that this is the B and this is the A, and A is y2 minus y1, the length of that edge of the rectangular surface, and B would be the depth into the fluid. It's hard to see, show these things. Okay? So the question is how do I calculate the resultant force? First of all, if I look at the distributed load, it has this shape. Mathematically, how do we describe that profile, the cross-sectional shape of that pressure field? It's a triangle. It's a trapezoid. You're right. You said trapezoid. Thank you. That's, it's one of these things that I always forget. What is the shape of that? Yeah, it's a triangle sitting on top of a rectangle. It's a trapezoid. Okay. Now, I'm going to do this. I'm going to take the mathematical approach. Okay? So what I was avoiding doing before, I'm going to do now for the more complicated case. And then you can always apply the more mathematical case to a planar surface, which is vertical. Planar surface is horizontal. Here's a planar surface at some orientation phi. So what I need to get an expression for the pressure as a function of y. Y is a axis. It's a coordinate. So what is it going to be? Can you get the pressure at any point as a function of y, where I would use it to evaluate y between y1 and y2? What would that expression look like? I'm going to stop and we'll walk around and we'll see how many people can get that. Help. So we have to get this down. This is the easy step. The rest is going to be really tough. I hate to say it. But is it going to be rho g times some depth h as a function of the distance going from the origin, y, Oh yeah, rho GH, but that H is, this is a right triangle. I have to see that right triangle, don't I? And isn't this the hypotenuse of the right triangle? Y, the distance from the origin, isn't that the hypotenuse? So H, the critical thing that I needed to replace, is Y times sine or cosine phi, sine or cosine phi, sine or cosine, sine, hey, maybe I should have thrown in tangent. Sine of phi, cosine phi, tangent of phi. No, you know it, it's the sine of phi. Do you like that? Once you see it, it's pretty easy, true? But you got to get it on your own. The next step is to say, I'm going to get a equation for the resultant force, F of R. And that equation for the resultant force is going to be some average pressure times area. We already talked about that. But what is this average pressure? Well, if I take the resultant force, that's the average pressure times the area, I could do this. I could say, give me the pressure at every little chunk of area and I'll sum them up. Does that equation make sense? Calculate the pressure at every little chunk of area and then sum it up. Well, the area dA is, let me break it up here, dA from calculus. Think about integrating over little strips because that strip is a distance dy. And what's the little dA for that strip? B dy, true? Or you could just leave it as dA. Let's just write it putting in the pressure. So we put in rho g sine of phi times y. That's all the pressure. And then I have dA. I'm going to leave it just like that for a minute. So this resultant force, or maybe I should do this one, the average pressure is equal to the integral rho g sine. You know what? That rho g sine, they all can come outside the integral because isn't rho constant? Isn't g constant? Isn't the sine of phi constant? Okay, so they all come outside the integral sign. Sine of phi, all of that. And then I'm going to have the 1 over the area, the integral of y dA. Did I make an error or did we follow? What is this term? From your experience, all those tough engineering classes and tough math classes, you can't even count up how many math classes you had to take and pass before you got here. You don't have enough fingers and toes if you go back to kindergarten and grade school. True? What is that term in the brackets? 1 over a integral y dA. It's equal to y sub c. Y sub c. What do you think the subscript C is for? Centroid. Centroid. That's what it is. That's what it is. Do you know this works no matter if the area looks like this? I just got to get the centroid of that area. It doesn't matter if the area looks like this. I got to get the centroid. It's got to be a planar area, not a curved surface, but a planar. That's all. So basically, we get our basic equation that the average pressure is rho g sine phi y centroid. It's just what we talked about. But I'm showing it more mathematically. It's the pressure, the average pressure is the pressure at the centroid of that submerged planar surface. Multiply that by the area, and you get the resultant force. Now, where do we stick that resultant force? Well, let me ask this question. Should I stick it right in the middle? No. Should I stick it at 1/3 up from the bottom? We're going to have a clicker question. So the clicker question is, if you think it should be stuck in this region right here, answer A. If you think it should be stuck right at 1/3, answer B. If you think it should be stuck somewhere in between 1/3 and a half, answer C. If you think it should be stuck right at 1/2, answer D. And if you think it's E, you just guessed wrong. But you can guess wrong. A, B, C, or D. And you got only 30 seconds. Where do I put it at? I know how to calculate the magnitude. Where do I place it? Yeah, we just all work in gauge pressure. Often air, it contributes to everything, adds atmospheric throughout. Well, it's all in the context of a problem. Fluid statics problems are...
So if I added it in that case, you just probably wouldn't count it wrong.
No, I wouldn't count it wrong. All right. All right. So the majority of people said, I don't think it's spot on at 1/3. Nobody said it's spot on at 1/2. Most of us think, you know what, it's between 1/3 and 1/2. Because it's a combination of a rectangular load, which would be at 1/2, and a triangular load, which would be at 1/3. True? So, congratulations to the 36 people, the 77%. Isn't that correct? Isn't that correct? Okay. So, how do I now determine mathematically where to stick it? I want to put it at a certain location. I'm going to describe putting it at a location YP. That's where I'm going to put it. Okay? And YP, is going to be between this value and that value. We agreed. It's somewhere in that range C. Okay? YP. Why did we use the subscript P for that Y? Why this P subscript on this Y? What am I trying to calculate? What would I call it? Center of pressure. Contrast that with YC. Centroid of the area. Got it? Somebody very mathematical said, Professor, why don't I just look at the cross-sectional area of this thing, calculate its centroid somewhere floating out here, I guess, and wouldn't that resultant force? Yes, it would. But let's just do this mathematically brute force. Okay? So if I'm going to do it mathematically brute force, how am I going to solve for y sub p? Sum of m's equal to 0. Good starting point. Sum of m about the point O. What does that mean? Let's start around this point right here, O. Okay? So the sum of the moments. So the distributed load has to have the same equivalent moment as the resultant force where it's placed. So the resultant force, F of R, needs to be replaced at y sub p. I'm going to now use this equation to solve for what y sub p is. Let me get it right here. The center of pressure, where I need to apply F of R. Okay, well then I have to say that it's going to be the same as doing the moment of a little distributed load. The moment of a force, just go back. What are the units on the moment of a force? Distance times force. True? So don't forget, put the distance and then the little df, the sum of little chunks of force. But the little chunks of force are due to the pressure and the little area strips, PdA. Okay, but a lot of students don't leave out the y because that's critical to the calculating the moment. And notice that each one of these little chunks are perpendicular to that distance, it's coming down. It's a planar problem. It's straight axis y. All right. So what is P? Can I replace P by one of the first things we had, rho g y sine of phi dA? Can I do that? Can I take the rho outside the integral? Take the g outside the integral. Take the sine of phi outside the integral. What's left inside the integral is rho g sine of phi is integral of y squared dA. I stare at that for a minute. I say, I passed the class called statics. I even got an A in statics. I learned a lot in statics. I liked statics. I recognize that term from statics. Or do I? What is that term from statics? I heard it. The moment of inertia. The moment of inertia. What symbol in statics did we use for the area moment of inertia? I. Very good. What? I double X. I even like that. Okay? I double X. Now, this is a little review. I remember two moments of inertia. One called the area moment of inertia, or they just said moment of inertia. The other one they called mass moment of inertia. Is there a difference? Yeah, there is a difference. The other one, let me do this. Sometimes units help me. What are the SI units of the area moment of inertia? I double X. Or just the moment of inertia. A lot of people would drop off the area term. It would be what? Kilogram meter squared is the perfect mass moment of inertia. But I'm looking for the moment of inertia, sometimes put the word area to contrast it between mass moment of inertia and area moment of inertia. So what are the units for the area moment of inertia? Meters to the fourth. Who said that? Perfect. Good. So this unit is meters to the fourth. How many people remember that? First time you see moment of inertia, it's crazy. You scratch your head. How can this parameter be of any use in anything in engineering? But it is. How many people took solids? Solids, they beat you up on this, true? They say, oh, I need the moment of inertia of an I-beam. I need the moment of inertia of this type of beam because you're trying to bend it, right? Okay, so here we have a little fluids, moment of inertia. So what I need to do is I need to calculate this moment of inertia. That's the equation for it. Is it around this x-axis axis running through the point O? Is that where I have to calculate it from? Is that our notation? Well, y is measured from here. Is measured 0 is the origin. Think about x is the axis running, like a right-handed coordinate system. It's perpendicular to the y-axis. It's coming out of the sheet. That's why we put it x. Hard to show, but there it is. Okay. Well, let me do this. Let me show you the formula for the y sub p. So this is y sub p. What is f of r? F of r. Let's replace it by what we calculated right up here. Isn't f of r equal to rho g sine of phi times what? Times y sub c? Is that true? F of r. That times an area. I got to pause. Did I rewrite f of r correctly? I see a couple head nods. When you give me a thumbs up, then I'll know that you confirmed it in your own brain. Yeah. Thomas is in with his yes. You're in. Anybody else? You're in. You're in. We got 2 more ins. 3 ins. Good. 4. Are we in? Professor, look at, you're getting paid. I'm paying. You just talk. Got it? I like these seats. I like this building. It's nice and air conditioned. Are we in? Okay, good. Now, okay, so what I do is I get this equation for y sub p. Notice that I can cancel some terms. It's going to simplify down. It's going to simplify down nicely, isn't it? So, it's not going to be so nice. Right now, if I'm going to get this I sub xx around this point O way up here, How am I going to do that? I remember I had some tables in solids and tables in the mechanics book, the dynamics book, as well as the statics book. And so I take a look and I go to a table like this and I say, remind me please the moment of inertia for some common areas. Let's say a rectangular area. Here's a semicircle, just to throw it in. Say, oh boy, there it is. Now, this is a notation, I think, out of the Hibbler book. Does it look familiar? And then in the Hibbler book, they have this equation, which is I sub x. I prefer the I sub xx. But guess what? Some people just use I sub x instead of different notation on the subscripting. That area moment of inertia for the x-axis, this axis going right through the C. What did they put the C there for? Centroid of that rectangle is 1/12 base height cubed. How many people remember 1/12 base height cubed? Good, good. That thing you don't have to memorize. This stuff, if you need it, it comes into the equation, you look it up. But some things, after you use it a few times, you kind of get a feeling, oh yeah, 1/12 base height cubed. Seen that a couple times. All right, so I would prefer that they write it like this, with the XX with the C. What do you mean with a C? The x-axis going through the centroid of that area. Because isn't this axis right here parallel to the x-axis? It's a different axis, but it's parallel. Isn't this axis right here parallel? That reminds me, we have a very famous theorem. I want to see if you can recall the parallel axis theorem. I'm going to walk around, take a pause. Some of you are yawning. It'll wake you up. And you write down from memory the parallel axis theorem. Got it? Parallel axis theorem. Let me fire this back up. All right, so some people had it. A lot of people wrote this. They say Ix through some other location. I don't know. Well, let's say some location that goes through the point O. Put the point O right here. Some other location, or just Ixx, okay? Is equal to Ixx comma C. Are these the same? Oh, they look the same except for one little itsy-bitsy difference in the subscripting. What's the C there meaning? It goes through the centroid. It's this one going through the centroid for that axis. But we can move it by increasing. And we add a factor which needs to have SI units of meters to the fourth, just like this has units of meters to the fourth. A lot of people were putting md squared. D I interpret as distance, perpendicular distance between the two axes. That would have meter. M I interpret as mass in kilogram. Is that correct? Professor, I changed it up. I use A for mass and M for area. You're 100% correct then. If you choose the symbol lowercase m for area, this is perfectly correct. Isn't it? But most people would want to avoid the confusion and they would put an A there. All right, Professor, what is exactly that A for this rectangular problem? Well, it's the area. Isn't that for this problem right here, B times H? True? And what is D? Perpendicular distance separating the two axes. Pardon? What?
H, because H would be completely the entire rectangle. So I guess if you're doing is a function of y, it would just be.
Well, it's about you have a moment of inertia about an axis. And what we want to do is move from this axis, which is often reported in textbooks, centroidal x-axis, to an arbitrary axis. Sometimes they move it to the edge. That's common. A lot of times it can be moved off of it. It doesn't have to be on the object. It can be well off the object. True? That axis. It just D gets bigger and bigger and bigger. Notice that this just adds. There's no way you can have a negative area just like a negative mass, you can't have it. And you can't have a negative distance squared. It's all going to be just increasing the moment of inertia. This I just throw in there because there's another one to look at. It's not that it's more applicable. So what we do is we come back to this problem and we say, I need to get this one right here. That's going to be IXXC, we understand that notation, plus the distance, okay, between what and what? Well, I needed it to go through the origin, that's the axis of interest, and it's going to go from the centroid to that new axis. What is that distance? Y sub c. Square it, multiplied by area. I've correctly applied the parallel axis theorem. True? Now I can simplify this a little bit. I'm sorry, I'm going to bring it down here because I'm running out of room. And so I'm going to clean it up. I have y sub c, a y sub p is equal to I x x through the centroid plus y sub c squared a. Did I do it okay? Did I simplify it? Or did I have an error? Then one more step, I'll put it like this. Y sub p, where, that's the center of pressure, where I need to put that resultant force for the correct application, for the correct moment, is equal to y sub c plus I xx divided by y sub c a. This class gets easier every minute. I like that equation. It's easy. Professor, is that equation on our equation sheet? Right there. We just derived it. First equation in chapter 3 that we put on our equation sheet. Did I write it correctly? Do you see it right there? Equation 3.22b. There it is. We have to understand each term, true? Professor, can I write little cheat sheet notes on my equation sheet explaining each term? No, because it says no notes allowed on this sheet. You just have to know it. I encourage you to have 2 sets of sheets, one full of your notes, one clean for exams. Okay? All right. Here's a question. I have the surface way up at the top. If it's that edge is at the top, it's not submerged, then I really have a triangular distributed load. And I try to put the half mark and the 1/3 mark. Where is the resultant force applied for that first top case? It's right at that 1/3 mark, true? But I go down some distance. I look at it. You know what? It's still a rectangular load and a triangular load on top. I think about the 1/2 mark and the 1/3 mark. Where is the resultant force placed for this system? Between the two. I then compare it to this one, which is really deep. Think about the force, the hydrostatic force acting on this submerged plate. Is it primarily uniform pressure over it, or does at the top of the plate versus the bottom of the plate have a big pressure difference between the top and bottom? Very small. The triangular part is very small. You could almost neglect it. So guess what? If I take a half and then I take a 1/3, right? Guess where the resultant force is? Very close to the half. Very close to the half. It starts to shift the location of y sub p, the center of pressure, shifts and gets closer to the center of the area, the centroid. True?
We consider that negligible, I guess.
A lot of engineering applications, you would make those mental checks to make sure that the computer code or your analysis isn't incorrect and that you understand that the results are trustworthy. So, here's a summary. We have a submerged planar surface. This equation, straight out of our equation sheet, we now understand. We can use it, but we can only use it for a planar surface that's submerged. There's a difference between y sub c. Oh, I forgot the name. What is the name of y sub c? The centroid of the submerged area. And y sub p, what is that one? Center of pressure. That's where I need to apply the resultant force. What is the equation for the resultant force? Calculate the pressure, not at the center of pressure. This is somewhat confusing. Calculate the pressure at the centroid of the area. That's the average pressure over the area. True? Calculate the pressure at the centroid, multiply that by the area, you got the resultant force. Next, use the I, area moment of inertia, and the parallel axis theorem to calculate the correct placement, the center of pressure, which is y sub c plus. And for this coordinate system as shown, it's always going to be below y, or beyond y sub c. Y sub p is always going to be a little further down that axis. See that? Okay, very good. Let's solve a problem. Calculate the force that the stop must exert on the bottom of the gate to hold the water back. So we have a gate, it's hinged right here, and it's in a water, holding back water on the left-hand side of the gate. The gate is colored red, and there's only a stop at the bottom. We'll assume the gate has a depth of 1 meter. 1 meter depth into the board, okay? Just everything per meter. So what we do is we think, okay, well, it's 3 meters down to the top where the hinge is, and then the gate's 4 meters. What's the total depth of the water? 7 meters. True? And what I want to do is I want to calculate first the magnitude of the resultant force, F of R. Well, is it that I get the pressure at the centroid of the area? Yep. Where is the center? What is the depth at the center? Well, it's 2 meters down from the hinge, which is 5 meters down. So the pressure at the centroid of it is going to be rho g times 5 meters. I know I'm mixing symbols with numeric values, but instead of introducing another h, and h1, h2, h3, h4, I'll do it that way. That'll be the pressure down there, true? And so what is the magnitude of rho g in SI units? I want to be quick during the exam. I want to be correct, but I want to be quick. I've done this rho g over and over again. 1,000 times 9.81, right? So I can put 9.81 kilonewton per meter cubed is the weight density of water. True or false? You don't believe it, the 3 significant digits. I know. G isn't 9.81 in this room. G is not. True? Is G a little greater in this room or less in this room? Because of our longitude, latitude, altitude, blah, blah, blah. Elevation, it's a little less. Okay. So, but we're going to stick with it. 5 meters times the area. What is the area of the gate? Well, it's 1 meter depth and it's 4 meters height. So the F of R comes in at 196.2 kilonewtons. Now, I get a free body diagram of that gate. I have the action of the hinge. I'm going to say, oh, that's point A, and so it's a sub y and a sub x. And I'm going to have the stop acting, the force of the stop right there, acting on the hinge. And I have this force due to the water, the resultant force, which I just calculated, 196.2 kilonewtons. But I really need to know where that force is applied on this gate. Okay? So I then calculate y sub p. Oh, I forgot. Center of pressure. That's right. That's what the name is. It's going to be measured from the centroid of the area and increasing depth by the, what is I, the XXC? It's the centroidal moment of inertia. centroidal area moment of inertia? The area moment of inertia for the axis going through the centroid? Some name like that, okay? All right. Then I divide by my y sub c and the area. Okay. Well, I look at, this is, the centroid is right in the middle, c. What is IXXC for this gate? IXXC 1/12. B in this case is 1 meter. H in this case is 4 meters cubed. True. That's correct. So we get the value for the IXX. What is the value of Y of C? 6 or 5? No, Y of C. 5 meters. True? Okay. What's the area? We already did the area is 4 meters squared. And then we calculate that Y sub P is 5.2667 meters, meaning measured from here down, it's a little bit beyond 5, it's 5.2667. That's what it is. Now, if I do now that I have where I apply it correctly at a depth of 5.2667 meters from the top of the surface of the water, I come down here and I'm going to know where I apply it right here, but I'm going to do a sum of the moments around this point, point A. If I do the sum of the moments around point A, and for equilibrium that has to equal 0 on this gate, I have that F of R times that distance. That distance, I know there's a lot of addition and subtraction, but what is that distance from A to the point of application of F of R? 5.2667 minus 3. So it's 2.2667 meters. True or false?
Yes.
It is true. Good. And then we have another balancing or trying to make it rotate in the other direction. The force of the stop, which I'm trying to calculate, times its distance, which is 4 meters. That's right. So what we do is we substitute, sorry I'm kind of mixing these up, but I'm trying to conserve space and go fast. I have 196.2 kilonewtons. We put that in there. And we can then solve for the force of the stop. The force of the stop is a whopping 111 kilonewton. Make sense?
Yes.
All right. So, ready to move on? There's another strategy. Instead of using all that calculus and those equations to calculate the mass moment of inertia, you can take a very brute force approach. And I would do that typically, right? I would say, you know what, this is made up of a rectangular and a triangular load. And I'll replace the rectangular load by a resultant force A, and I know that's right in the middle. And I'll take the triangular load, and I know it's force B, and it's replaced at 1/3 up. And then I'll take those two forces, and then I'll put them into an equivalent force if I want a separate force, or I'll just keep two forces due to hydrostatics in my calculations. This is an alternative approach. It works. It just may or may not be easier for you. Okay? But that's, this is the value for F of A. This is the value for the pressure at A at the centroid of A. This is the pressure at the centroid of B, etc. Okay? All right. All right. What about submerged curved surface? The key word, we have a curved surface. Now, you can beef up your calculus, and you could do two-dimensional, spatial, and volume integrals, and it's really a challenge. Or you can try to do something which may be a little more insightful to help solve a problem. So let's say I have a container, and over here I have a wall that's curved and a section of the wall right here that may be curved as well. I'm trying to show it curved. Let me do it like this. I don't know. Show it like that. And then the wall continues on. And then we have fluid. True? I didn't want to make it too complex, but don't make it flat. Make it curved. I don't like that at all. Here. Boom. Now I'll finish my wall. There. Okay? There. That's my curved surface. It's a section of the side of the tank. Now, I would know that the pressure is always acting perpendicular to the surface. Make sense? Always the pressure is perpendicular, pushing, perpendicular to the surface. Okay. To solve this problem, which would be, maybe you want to ask, what is the resultant force? And I would do that as a vector sum resultant force component in the x and some resultant force in the y for this problem. That's acting on this surface, f of rx and f of ry, pushing it. Okay, and then I would want to know, okay, where does it go through? Some line of action of this resultant force that the water's pushing on this red gate, this red curved surface. Okay, fine. The way I would do that, in the way it's outlined in the textbook, is cut and do a free body diagram. Do a free body diagram of a chunk of fluid. This fluid has the red curved surface as one of the boundaries, and the other are imaginary surfaces which are just cut through the fluid. Okay? Now, I then go and I look and say that chunk of fluid inside my, this enclosure is at rest. And the fluid that's outside of it exerts some forces on it. So this surface right here has a trapezoidal pressure distribution acting on that face. And because I cut it along an axis, along the y-axis, it's just pushing in the x direction. True? And because I cut the bottom one horizontal, the force due to the pressure of the water below is acting upward, and it's pushing with a uniform distribution. So what I can do with a lot of work is I can replace and I can get a force that the water's doing on the outside in the horizontal direction, and a force that the water exerts on this system in the vertical direction with a lot of work. True? Can you see the approach? And then I say from statics, sum of the forces in the x must equal to 0. Well, if the water's pushing on the gate's pushing back on the water with f of rx and pushing down with f of ry. True? Equal and opposite forces. Water's pushing on the gate, gate's pushing back on the water. It's in static equilibrium. So in the x direction, we get that FH is in the positive, FRX is in the negative, in equilibrium. So now I can calculate at least the x component of the resultant force that the water puts on the gate. Do the sum of the forces in the y. What's that give me? Well, don't forget the weight of the fluid in our force balance. So we'll have that F of V pushing up is the weight down plus F of Ry pushing down. Let me just summarize. A lot of work, but once you get it, you get the answer you're looking for typically is what is the force that the water exerts on a curved surface, a submerged curved surface. Make sense? Do we have time for a problem? It's a long problem. It's a tough problem, but let's jump into it. Maybe I can solve it in the time period. We have a long solid cylinder of radius 1 meter. So there's the radius. And its length is 3 meters. So I'm not showing 3 meters in the illustration, but that's the depth, that's the length of it along the axis of the cylinder. It's hinged at point A. Do you see where point A is? And it's hinged. Does a hinge offer any resistance to rotation around the hinge? No. But the hinge can exert a force in the X or in the Y to hold that point at that location. All right. When the water level reaches 8 meters, then the cylindrical gate opens by turning about the hinge at point A. So if the water level is low, it sits on the floor and seals. And if you do a free body diagram of the cylinder, there is some force that the floor or the ceiling or the concrete floor has to exert to hold up the cylinder. But as the water level rises, what happens? It gets to the point where if it's above 8 meters, it goes to 0 when the water is at 8 meters. That's what they're saying. And now it'll pivot up and water will come out. Okay? So when the water level reaches 8 meters, the cylindrical gate opens by turning about the hinge at point A. That's another way of saying R goes to 0. The force on the bottom of the cylinder to hold it up goes to 0 at that point. Part A, Part B, and Part C. So for Part A, the hydrostatic force acting on the cylinder at that point. All right? Part B, its line of action when the gate opens. So, I need to know not only the magnitude, but its line of action. Once I know the line of action, I know basically the whole thing about that force. Okay? And then C, the weight of the cylinder. So let's bust it down step by step. Part A, the hydrostatic force acting on the cylinder. Well, if I take and look at this chunk of the cylinder right here, right? I pull it off and I look at it right here. I'm just interested, the force of the pressure is always perpendicular to the local area. True? There's something common about this little force acting on this chunk of area and this chunk of area and this chunk of area, this chunk of area. They all have a line of action that goes through the center. Don't they? We're going to need that. We're going to use that in a minute because that'll help us with Part B, that's line of action, because we know that the resultant force, that the hydrostatic force acting on that cylinder goes through the center. Now, it could go through like this, or it could go through like this, it could go through like that. That's something we have to calculate. All right. Now, we can do this is if the water's pushing on this curved surface, then I can take and turn it around and use that curved surface to say that pushes on a chunk of water that I'm going to cut out right here. So we cut out a chunk that looks like that. This is of water. And let's do now a free body diagram of that water. Don't forget the weight of the water. And that weight of the water acts at the centroid of that funny shaped area. All right? Good. We have the resultant force that is from the cylinder onto the water, and I can bust it into two forces. It's going to be the force resultant. Let me look at my notation here so I don't mess it up. The force resultant in the X and the force resultant in the Y. Okay? Now, over here I have a hydrostatic pressure distribution. True? Isn't that cutting on this surface right here some hydrostatic pressure distribution. And on the bottom, I have a uniform pressure distribution acting up. Just like we described. True? Okay. So, let's do this. What is the magnitude of the hydrostatic force pushing in the horizontal direction? And what is the magnitude of the hydrostatic force pushing in the vertical direction? And what is the weight? The weight. Okay. Because if I say I have all of these, I do the sum of the forces and the x must equal to 0 for static equilibrium of this system, I get an equation that says f of h is equal to f of r sub x. I get f of h. I then know from sum of the forces in x it's equal to f of rx. True? And then sum of the forces in the y, we know that f of v minus w is equal to f of ry. So if I want to get the two components, f of x and f of y, that's how I get them. I know they go through the point, the center of that cylinder, and I don't know the orientation, but once I know the orientation, let me draw it like this. I put a little vector, maybe I show it like this. F of rx, f of ry. I put a little right triangle. I put an angle phi right there. So not only do I know a line at which it goes through, I can calculate the angle phi. How do I calculate that angle phi? Arc tangent, inverse tangent. That's right. Fry over frx. There's the roadmap for the first two parts of this problem. Make sense? You ready to slug through it? Let's slug through it, see how far we get. Let's get maybe the weight of this chunk of water. That W right there. That's what I'm looking to calculate. How do I calculate the weight of the chunk? Yeah, what I have to do is I have to get the volume. I get the volume multiplied the density times the volume times G. Okay. Okay, the density of water is easy. The volume is a little tricky. What I do is come over here and I think of, I take a 1 by 1. Let me do it this way. Do it like this. Can you see what I'm trying to do? I'll do a 1 by 1 box, right? And then I'll subtract off a quarter of a circle of radius 1. So it's going to be, the volume is going to be a 1 by 1 meter minus 1/4 of pi r squared. That makes sense? Don't go to sleep on me. Are you with me? That's right. And then we have the depth of 3 meters. I'm going to put, I don't know, should I introduce a symbol for that or just put 3 meters? Put 3 meters. Put 1,000 right here, kilograms per meter cubed. And then put 9.81 meters per second squared. And then you calculate the weight, and the weight comes in at 6.316 kilonewton. I'm going to pause. I want somebody to take their calculator and verify this. So we confirm that. Now, what about the next easiest one, maybe F of V? Well, I get the pressure, right, at the bottom. That's going to be rho G times the 8 meter depth. Isn't the bottom all at 8 meters? And then I say, what's the area? Well, it's 1 meter by 3 meters. True? Is that F of V? And so if you calculate F of V, we get 235.4 kilonewtons. I just did W, did F of V. we now know the result for f of ry. F of ry comes in at 229.1 kilonewton. Okay? Now, this one's the hard one, f of rx. How do I calculate f of rx? Or, I'm sorry, f of h. F of h is, we calculate that. It's going to be, get the centroid of this area right here. What is the centroid of that area? Okay, remember, there's a difference between the centroid and the center of pressure. Am I asking you to give me the center of pressure or the centroid? The centroid. Okay. Is that centroid at a distance 7.5, or is it 7, or is it 8? What is it? What is the that distance down for the centroid? 7.5. Okay. So this is going to be rho g 7.5 times 3 meters. And when you calculate that, it comes in right at 220.7 kilonewton. Now, I should have said it's hard if I want to get the correct placement of it. The magnitude's easy. We just got the magnitude. Guess what? In the interest of time, I'm going to share with you. You don't need to know the correct placement of it right now. Okay? Let's do this. Oh, boy. Okay, so basically I calculate these two components, so I get the f of r maximum, or the magnitude is f of rx squared plus f of ry squared square root. And so the resultant force has a magnitude of 318 kilonewtons. That's part of the answer for part A. For part B, it's line of action when it passes, when the gate opens. Well, first of all, we will describe that line of action as going through this point of the cylinder by the angle phi. We already talked about that angle phi. And so that phi, when I calculate inverse tangent, it comes in at 46.1 degrees. 46.1 degrees. Now for part C, what we do is we shift our focus away from the water and that little half moon or sliver, and we focus on the cylinder. All right? So here is my cylinder free body diagram. I have the weight of the cylinder acting that way. True or false? I have a force, the hydrostatic force, made up of two components, but they go through the line of action which goes right through the middle of that cylinder. So, using the principle of transmissibility, I can put that f of rx and f of ry could be transmitted, principle of transmissibility, to be applied right at the middle of that, even though it's due to this distributed hydrostatic load from the hinge A to the floor. What principle was that? Transmissibility. It's a good principle. Take a look at it. I know that you use it all the time. This is the point A where we have this hinge exerting a of x as well as a of y. True? And what about at the floor? Well, we said R goes to 0. I know these two components. I can get the weight. This is a different weight. This is now the weight of the cylinder. But guess what I'm asked to calculate? The weight of the cylinder. That's what I'm asked to calculate. How would I calculate W? What's the strategy? Do the sum of the moments around the point A, the hinge. And when you do the sum of the moments around the point A for the hinge, you find that the weight at a distance 1 meter off, acting downward, is f of ry at a distance 1 meter, acting upward. Does f of rx contribute a moment about the point A? No, it doesn't. So this really boils down to a very simple, the weight is equal to 229 kilonewtons. It's almost too easy. But the concepts are difficult. The math is easy, the concepts tricky. I pause. Any questions? Let me ask you this question. Professor, what's happening Friday of this week? What's happening Friday? Exam. So hopefully nobody will say, I didn't know that we have an exam. Yeah, well, okay, I've mentioned it a couple times. Thank you very much. We'll see you on Thursday.